So for this particular video, I do want to give a shout out to Jacqueline Liu, LUU, class 2006 at Garden Grove. She caught my little error, so here I am doing a second take on this one. All right, so here we have a 10 kilogram bullet. It is fired into a 1200 gram wooden block that is initially hanging from 150 centimeter long string. And then it's just the bullet gets stuck in the block, and then it's gonna swing to an angle of 40 degrees after the collision. All right. So part A wants us to find the speed of the bullet immediately after the collision, and part B wants us to find the speed of the bullet before it strikes the wooden block. All right. So this is a backward problem. So let's go and crank it out. In order to find the speed of the bullet or bullet block system after the collision, you have to use conservation of energy. So you notice here on the diagram, you have this bullet block system that comes to a rest after it has risen some height after collision. So here, I'm just going to call this PF, and I'm just going to this KEI being the reference point immediately after the bullet is embedded into the wooden block. So all this kinetic energy will be converted to gravitational potential energy. So I'm just going to say KEI will be converted to PEF, and then I'm just going to break up KEI into 1/2 M bullet plus M wooden because it's embedded, so it moves as one system, and then VI square. And then here on the right side, PE is just MGH, but M being the mass of the bullet and the wooden block together because they now move as one. But it doesn't matter because MB plus MW will cancel on both sides. So really, at the end of the day, we simply have VI square times 1/2 equals GH. But then to solve for VI square, I need to multiply both sides by 2 to cancel out this 1/2. Hence, the 1/2 now looks like a 2 on the right side. Okay, so, or you can just literally think about it. You can just move this 2 in the denominator on the left hand side to the right side, and that's what you do when you multiply by 2. All right. Other than that, I do recognize that this is VI squared, so to get VI by itself, you need to square root both sides. So here, this is 2GHF. However, what I don't know is I don't know HF. G is just simply 9.8 due to gravity at the surface of the planet. I don't know what HF is, but I can figure out HF using a little geometry. So here in the schematic, I'm just going to label this H or HF, however you want it. Okay, so that H length is super easy to calculate as long as you keep up with the geometry here. All right, so here I'm just going to shade in this right triangle. The length of the string needs to stay constant. The length of the string in the diagram here in the problem, it states that it's 150 centimeters, which has been converted to 1.5 meters for you. So this is the right triangle. The hypotenuse is L, which is 1.5 meters. And then to find H, I need to figure out what this orange arrow is, the length of this right triangle, the adjacent side. And this is the adjacent side of this right triangle, so it'll just be L cosine theta. It's cosine because it is adjacent. All right, other than that, I know the whole entire length of the string is 1.5 meters as indicated in the diagram. So from the pivot all the way to where the wooden block hangs is the length of L. Well, I just found the length of this right triangle here to be L cosine theta. So using common sense, I can just go ahead and find H. H would just simply be the whole entire length, which is L, minus L cosine theta, and then that equals to H. All right. So I want to make the statement H is simply L minus L cosine theta. Well, once I know what H is, I can simply plug it in for this function here underneath the radical sign. So VI is simply the radical of 2GH, H being L minus L cosine theta. Make sure you use parentheses so your calculator is not whack. All right, I'm just going to plug values in. Here's the 2 that I carry down. G is positive 9, or in this case, it's just 9.8 because we're dealing with energy here. All right, other than that, L being 1.5 meters. L here is 1.5 meters times cosine of 40. And if you simplify this properly in your calculator, you get a value of 6.88. But then we need to square root the 6.88, which will give us a positive or minus 2.62. But the question here in part A asks for speed, so I don't really need the direction. So I'm just going to delete plus or minus. So my answer would just simply be 2.62 meters per second. And that is the speed of the block or bullet block system right after it got struck. All right, so that's the answer to part A. To do part B, well, it asks you what was the initial speed of the bullet. So now we have to set up conservation of momentum. So here in the diagram, I labeled the initial speed of the bullet as VBI here. All right, so again, the mass of the bullet is given in 10 grams, but 10 gram has been converted for you into 0.01 kilograms. Likewise with the mass of the block. The mass of the block initially in the statement is given as 1,200 grams, but it's important that you understand and pay attention to units. You need to convert grams to kilograms. So here, 1,200 gram has been converted to 1.2 kilograms for you. All right. If it's not, make sure you convert it for yourself. So here I'm just going to set up momentum initially equals momentum final. Initially, there's only one object moving, that is the bullet. Here, M bullet is 0.01 and it's moving at some speed or velocity of VBI to the right. And then after it collides and gets embedded into the block, it's stuck in there. So therefore on the right side, I have mass of the bullet plus mass of the wood in parentheses because now it moves as 1. And you notice here in my work, I have VF highlighted because VF doesn't have a subscript because they move as one system. All right. Other than that, it is now just plug and chug time really. To get VBI by itself, I need to divide both sides by the mass of the bullet. And that's what I did here, which brings M bullet to the denominator on the right side. I have all the values. The mass of the bullet is 0.01 kilograms. The mass of the wooden block is 1.2 kilograms. And then the final speed that I found immediately after collision is from part A, which is 2.62 meters per second. And then divide that by the mass of the bullet, which will give me a value of 317.02 meters per second. And once again, part B says what is the initial speed because it uses the phrase speed. I don't need to give you a direction. So the answer would simply be 317.02 meters per second. All right. So overall, just to recap, in order to find the original launch speed of the bullet, you had to use conservation of energy after it collides, and then you had to use conservation of momentum just when it collides. All right. Stay whack. Excuse me. Don't be whack. Stay nerdy.